So actually, maybe Madison, because you're so when like that's a good question. Let's do this kind of a tag team thing and make sure that we're on the same page. Because I think you're saying what everyone else is thinking, and so if you and I are in more or less mutual agreement, we'll bring a whole lot of people along with us. Does that work for you, or is this asking way too much of you?
I'm being so serious. Like, if you give me a problem, I'm not going to know how to
let's just make sure
start
it's a problem that we kind of want to think about. So from the last class, we're talking about carbocations and water and acid. So let's follow up from last class. Okay, it's just if you have the full right to say, you know what, I prefer not to do this. If somebody else wants to step in and be a volunteer here to work through this orally, that'll be great. Otherwise, I'll try. But then what I need is people to interrupt me. So just jump in. And Samara's keeping an eye on the chat, and so Samara can yell at me from the chat channel. Yeah, Madison, go ahead.
I'm just gonna guess. So wouldn't the H plus attack? Oh wait, no, never mind.
No.
Disregard.
Go ahead.
At first, I was gonna say when the H plus want to attack that double bond, but then that carbon is a plus charge, so a plus with a plus wouldn't make sense.
Well, the double bond right now isn't plus at all, it's neutral. The double bond has no charge right now. So I like your thinking about the double bond attacking the hydrogen. That you're right. So if we draw that, just like you just said, and maybe it might help just for a second. I'm going to draw in the hydrogens just so we keep track. So this is the exact, I'm just drawing the same thing again, but just with the hydrogens there, in case we're losing track of bonds and atoms. Okay, so we have the double bond attacking the hydrogen. I like that. So that means we have two possibilities, or two products that you can get from that arrow. Yeah, this is a carbocation, and it's in ethanol, not water, but it's the same thing. So we have two possibilities to think about. One is, and let's color this H, this new H that we just added, let's color it blue so we keep track of it. Okay, drawing in all the atoms that were there earlier, they're all still there. So one possibility is we can put the carbocation there, and the carbocation is there because the electrons in the double bond were used to make the bond with the hydrogen. And there are two electrons there, and those two electrons bond to the H plus, and that leaves the other carbon without electrons, and so it's positive. The other possibility we have is that. And so whenever you're doing a problem like this, whenever you're adding something to a double bond like this, whether you do it in your head or on paper, you're going to need to think about the two possibilities. Which side attacks? So the question that then comes, which one of these forms is which one of these is more stable? Better to have the positive charge on the right structure? Yes. Okay, so we have a bunch of answers here. So, double bond with oxygen. Okay, so we have people focusing on resonance. We have people focusing on the fact that the carbon is secondary. The carbon is technically correct. You should all watch Futurama. Technically correct is the best type of correct. Technically, that carbon is primary because it's only attached to one other carbon. Functionally, as far as hyperconjugation goes, it's secondary because it's attached to two atoms that have sp orbitals. So yeah, so on hyperconjugation, this one's better. But then we have the better points, which is on res. Oh, I set a background on my teams. I did not intend to do that. That's a nice background. I'll leave it. You also have resonance. Okay, so both factors, both resonance and hyperconjugation, favor the guy on the right. Which one's more important? Which one is the one that's really saying, yeah, it's this one? Like they both favor it, but let's say they favored opposite examples. Which one would be more important? Resonance, absolutely, Carolyn. Perfect. Resonance, everyone has their full octet in this example. It's a really stable resonance form. Do I have you, Madison, or have I lost you? You're my canary. Oh, good. Okay, so this is your stable form. Great. Now, we have a carbocation. I think the sentence didn't finish, Emily. Oh, okay. I wandered into a forest this morning. It's a forest of the mind. Yeah, resonance does dominate. Hyperconjugation is of secondary importance. Okay, so okay, we got just like dots and shit. So we've got this. Then the next thing is, second thing you should ask yourself now is this done? You've drawn an arrow. It's not. It's positively charged. There's no way we're done. Okay. Now we have a carbocation. We need a nucleophile. Two things to consider which nucleophile to use, because we have several here, is which one is the most reactive and which one's the most plentiful. Because those two things go together, right? You can have something that's really, really reactive, but there's only a tiny amount of it, so it doesn't matter. Or you can have something that's really, really plentiful, but if it's not at all reactive, it doesn't matter. We have something here that's pretty reactive and very plentiful. Yes, Christian, ethanol, it's a solvent, it's reactive. Now, reactive is always relative, right? Things are reactive in a given situation. Like $500 is a lot of money in a given situation. $500 is a lot of money when you're at a convenience store. $500 is not a lot of money when you're at a car dealership. So, but carbocations are very reactive, so you don't need a super reactive nucleophile. You've got tons of ethanol because it's your solvent. By definition, it's solvent. You've got tons because you're swimming in it. And then you react that. Now, because we've drawn resonance structures, it can be a little tricky sometimes to identify where you're going to make the bond. So again, this is the more stable form of the resonance structure. do we react at the more stable form of the resonance structure? Am I going to attack the oxygen with my nucleophile? Come back to that, Amanda, and I'll try and answer it. The second one reacts. Yeah, you attack at carbon. You always attack at the second most stable resonance structure. If you have resonance structures, they react as if they are their second most stable form. If you try and attack the oxygen, you'll run into all sorts of charge problems pretty quickly, and you'll realize you're screwed and you did something wrong, because you'll have like negatives and positives, you'll have multiple charges, oxygen will be making 3 bonds, it'll all be a mess. But if we attack at the carbon, we get that. We're not done yet because we're charged. You can't be charged. So we're going to make use of ethanol to strip away that final hydrogen. And we get our product. Now this is an acetal, but it's an acetal. We just were doing acetals earlier, but it's an acetal in the presence of ethanol. This is the end of the road for it. Okay. Yeah, so Amanda said, so why do we attack the second most stable resonance structure? Is there other than the most stable produce a lot of charges? No, not necessarily. I want to give an example of that. So let's say all molecules that do resonance react via their second most stable resonance structure. So if we take another example, this guy here, and I add H+, this is the most stable resonance structure of that molecule. Everything's neutral. The second most stable resonance structure is not the one I was going to draw, which was wrong. Is that. The reason is that the most stable resonance structure is normally uncharged, or it's a resonance stabilized charge. And what we've done is we've kind of masked it and stabilized everything. Whereas the second most stable one is almost always where the charges are going to react from. And I'm trying to think why this works. And I don't actually know if there's a good theoretical underpinning for it. I think it's empirical. I think it works because it works, in that you don't need to do this. If you can figure it all out, you can skip this whole thing about second most stable resonance structure and just go from the most stable one and figure it out afterwards. But the second most stable resonance structure normally has your best charge separation that's slightly unstable, and that's how you're going to react. Where did the hydrogen go? Oh, it's still there. I just didn't, like, the CH3s, it's all still there. And that hydrogen up there is, it didn't get deleted, it just got implicitly, it got implicitized. It was implicit because, you know, hydrogen on carbon, you don't need to draw them. And we don't normally bother drawing these byproducts. Yeah, so finishing the thought on the second most stable resonance structure, it's normally where we have the charges separated in the most logical way. Normally the most stable resonance structure, you don't have that. And I think that's universal. I can't think of any counterexample. Now there are examples where there is no resonance possible, in which case, you know, you react from the thing you've got where there's no resonance. Second point, why do we know that ethanol is reactive? Okay, ethanol is not always reactive. It's completely appropriate if you go, what's going on here? Why is this reactive here this time and not this time? Yeah, those are really good questions. And so what we have to figure out always, everything is relative to other things. This initial reaction, what we do is react with the most reactive thing first, which is H+. That's easy. It's the only charged thing. Now, you could react it with either of the oxygens there. Nothing would happen. You would do that. You'd stick it on there and you go, okay, now what? There's nothing that can go on if you attack it to one of the oxygens. But if you attack it with the double bond like we've done here, and as we've been talking about now for a little bit, then we can generate one of these carbocations. And carbocations are really, really, really reactive because C+ does not want to be C+. So it wants to be stabilized by something. And we are swimming in a bath of ethanol, and there are lone pairs on those oxygens. And the hydrogen on ethanol, just like the hydrogen on water, isn't really all that tight. Like the OH bond is a suggestion of a bond. It's covalent, but it's not, it's bouncing on and off all the time. So just like water is always in equilibrium with hydronium and hydroxide, that's the whole pH thing, ethanol is also in equilibrium with ethonium and ethoxide. And so the electrons on oxygen on the ethanol are pretty available. And so those lone pairs can attack. And there's no other really good option. There's a lot less of the starting material, which has an oxygen. And it's the oxygen in the starting material looks a lot like the oxygen in ethanol. Like it's, it's an oxygen making two bonds. So similar kinds of reactivity. It's just there's so much ethanol because it's your solvent. There's just so much of it. Like if you've done any of the in class labs, like the in-person labs, you pour in tons of solvent and you weigh out a little bit of other stuff. There's a lot of solvent. So if your solvent can react, your solvent does react. And I think we're seeing an example of that here. We've seen an example of it with the water stuff so far. Alyssa, do we need to call an acetal? No, not at all. I just said it was an acetal in case somebody's thinking about patterns. You don't need names for these things. I hate the names too. Okay, so Melitza said the way I think of it is because we have an abundance of H, it drives ethanol to be ethanol, not ethoxide instead, which means the nucleophile is ethanol, not ethoxide. My logic might be wrong though. Your logic is not wrong, Melitza. You're absolutely bang on. If you have H pluses present, you can't have O minuses. Because the first thing that's going to happen is the O minus is going to react with the H plus. Because acid-base reactions are the fastest reactions. We're going to see some more examples of that, but acid-base reactions happen first, always. So if you have if you have a bunch of O minuses and a bunch of H pluses, they'll react first, and we'll see who there's still more of at the end, and that's going to be the thing that determines reactivity. So you can't have ethoxide and H plus in the same time. So in this case, we have H plus, so we can't have any ethoxide, the O minus. So we need to use neutral ethanol. Notice I don't generate any negative charges here. Everything's positive because I start with H plus. If I start with a negative charge, we're going to see some examples of that. Then everything will be negative and I wouldn't see any positive charges. Yes, so Amanda said, do we use ethanol twice? Yes. So we used ethanol once as a nucleophile and a second time as a base to recover and get rid of this extra proton. How do you know what reacts first? The most reactive thing. Deal with the positive charge. Deal with the charges. Always deal with the charges. Always deal with the what is, and because we're going to see an example in a moment, which isn't charged and it's the most reactive thing. So always deal with the most reactive thing. The most reactive thing is almost always a charge. So wherever your charge is, that's what you got to deal with next. So in every step, we're almost always dealing directly with the charge. So in this first thing, we're dealing with the charge. The double bonds reacting with H plus. Then we generate carbocation. Our next step is we attack the carbocation, dealing with the charge. Our next step is we remove the charge by dealing with ethanol. So in each case, we're resolving the charge. We're really focusing on the charge, and that's always the case. Let's try a different example and see if any of this makes sense or helps. Okay. Well, we can finish this one. So give this a go. Oh, there's no, I need a nucleophile. That would help. So hopefully what you drew was something like this. And then this reacts with water. And it's still charged, so we need to get rid of that. So we're going to treat that with a bit of water. And so we can get that happening. So actually, I had drawn something that is true. Initially, I wrote this question weird, didn't put a nucleophile in, but we can actually draw what the chemistry would be in this case. You just need to think a little bit more broadly about what a nucleophile is. So this mechanism would be called a Markovnikov. This is still what we're talking about. So these are still Markovnikov additions. Addition of water. So we've done a Markovnikov addition of alcohol. We've done them of water. So if I drew this example down here, so all I've done is we've removed the solvent. There is no solvent. Isoprene is its own solvent. This guy here. That's not isoprene. That's 2-butene or isobutene. Isobutene. There we go. This is actually so as a clue, what I've drawn here is a major component of a lot of the plastics that are around me right now in my computers and laptops and things. And this is actually how we make these plastics. So remember what a plastic is. That might help figure out what's going on. Does anyone have a suggestion on what's going on here? It's cool. Come on. For a very limited definition of cool. Okay, well, hopefully the first step. Hopefully, no, this is okay. You generate a carbocation. So yeah, so exactly. So that's our first step. Exactly, Madison. Okay, so here what we've done every single time now is we've had a nucleophile to attack the carbocation. Still going to do the same thing, but what's our nucleophile now? Nope, no water. There's no water, there's no alcohol, there's no water. Everything that's there is there. There's isoprene and catalytic H+, just a little bit of H+. Normally you do this, you take a giant tank of isoprene, you know, maybe a kiloton, and you add in like a milliliter of sulfuric acid itself as a solvent. Will it attack itself? Yes, it will. That's exactly what happens. So we have another equivalent of the same thing, and it can attack. Double bonds are nucleophiles. Now, in the other cases, the oxygen was a better nucleophile, so the oxygen won. Double bonds are not great nucleophiles, but there's no other option. So I fucked it up. So we get that. And then guess what? It does it again. And you do this a few 10,000 more times, and you get plastic. So we're going to come back to this at the end of the class on how you can make plastics. This is called cationic polymerization. It's much rarer now, but still, if there's no other nucleophile present, the double bond can be a nucleophile in and of itself. Why is it attacking itself? Because no one else is there to attack it. And the carbocation needs to do something. So with nothing else present, there's no other option. But that's kind of like a little bit of a sidebar. It's not really central to what we're kind of discussing. I don't think I have any examples like that in the assignment. It's just even when I draw something wrong, there's normally an answer. No, it's not going to be charged at the end. It's going to do some termination steps. We'll get to that later. But we haven't covered the chemistry of how you're going to deal with that. I want to talk about a different example, though. I want to talk about a little bit of a weird example. Okay. Now, there's heat. There's our good friend isoprene. And there's molecular iodine, like I2. The first time you see this, it's really hard to see. So I'll walk it through it here. Heteroatom bonds are weak. Iodine bonds are particularly weak. Like the entire reason why iodine or chlorine are good disinfectants, like I2Cl2, is because all it takes is a tiny little bit of sunlight and boom, they rip themselves open, they start reacting with things and killing stuff. So that's why, you know, you rub iodine on yourself when you are going in for surgery or you fall off play structures a lot of as a kid. I was basically yellow for most of my childhood because of all the iodine. So this bond is really polarized. So at any given moment, arbitrarily, one of the iodines is pulling electrons closer to it than the other iodine is. It's completely arbitrary. It's completely random. It's just a really, really weak iodine bond. And that's because we can think of the iodine-iodine bond as kind of being in equilibrium with I plus, I minus. You know, they remake the bond, they break the bond, they remake the bond, they break the bond. Okay. The bond isn't polar. So Amanda said if they have the same electronegativity, how is the bond polar? Bond's not polar. But when it gets closer to something else, it induces polarity. Because again, what we have to remember is that the iodine-iodine bond, if we think about it, it's got this electron cloud around it. That's what the molecular orbital looks like, right? That's what they all look like. It's like a cloud. And at any given moment, that cloud is not symmetric. It might look like that. So there's fewer electrons here, there's more electrons here. I don't know what LDF means, and I really should. Okay, so what we have though is we just have London dispersion forces. I thought it was like, yeah, okay, yeah. I don't know. I thought it was some like text abbreviation speech that I didn't know. I'm old. I don't know all of them. So at any given moment, we do have this, and I was guessing what F stood for, knowing that what F normally stands for in those abbreviations. Which would still be probably completely correct. We have this breaking, like the iodine bond is really shaky. The iodines are really shaking each other apart, and like one's becoming positive, one's becoming negative. Split second later, they switch places, then they switch, but it's not normally completely even. Okay, just giving you some information about that. Now we have a reaction. I'm going to say this does react. It does something. Let's work through it using exactly what we've talked about. So can we identify the most reactive thing here? I've been talking about it a lot. So we're going to react with the most reactive thing. So can anyone guess what the first arrow would be here? Yeah, okay, the II is the most reactive thing. I agree. From double bond to I plus, let's do it. So if we're doing that, iodine can only make, well, iodine can actually make more than one bond, which is the secret, unlike hydrogen, right? Because iodine's got more orbitals. But let's break a bond. Because I minus is good, I plus not so good. We don't want I pluses around if we can avoid it. Okay. Iodine's almost like a sideways H. And we have I minus as well. So the most reactive thing is the thing that gets attacked. Yes, or the thing that does the attacking depending on the situation. In this case, our alkenes are our nucleophiles, so they're not very reactive. So in all the examples being here, you're absolutely right, Amanda. But we will see examples where it's inverted, where the most reactive thing is the thing doing the attacking. But the most reactive thing is the thing involved in the first step, because it's the most reactive thing. So it's going to be involved when you do the first reaction because it's the most reactive. Why are we attacking the I plus and not the I minus? Because electrons seek positive charges. And if the I minus already has lots of electrons, it's not going to want more electrons. Because double bond is basically us throwing electrons from a double bond at a nucleus. And if that nucleus is already negatively charged, it's going to just, our electrons are just going to bounce off. Yeah, there we go. Chitra just said, so what did I say about how heteroatom bonds, can we always assume they're going to be the most reactive? I can think of a couple of counterexamples, but for the purposes of this course, yes. Unless there's something like charged, if everything's neutral, it's the heteroatom bonds that are going to be your weak bonds. So if there's a charge lying around, deal with the charge. The charge is more reactive. But in all other cases, it's the heteroatom bonds. Nitrogen oxygen bonds can be stable under certain circumstances. But I'm not going to show any examples of nitrogen oxygen bonds in this course. Okay, so we get this. Now, can somebody guess what the next arrow is going to be? Okay, does the positive carbon now bond to the negative iodine from charge to I minus? Yes, I'm just going to invert your language a little bit. You're both right. Let's do I minus the charge or the negative iodine to the carbocation. Let's always try and, you're not wrong at all. The convention is always to say that the charges, the negative charges are the ones that are migrating and moving. Because that's the electrons, and the electrons are the ones doing the attacking and the interacting. The charges are, like positive charges are passive. Like positive charges are more a void, like they're a lack of electrons. Whereas electrons are the things doing the chemistry. So the negative charges or the electron-rich things are the things that are always moving. So you would do it right if you drew the arrow right. So charges go from negative to positive, because positive is the sink missing. It's blackness, despair, feeling when you have a midterm the next day. No, we have no charges. We're done. Our molecule is neutral. That was almost not painful. Okay. But it's not that easy. It's right. That's right. But it's not quite this easy. Does it draw which side? Does it matter which side we draw? So am I in up? I think this thing up here. Is that what you mean, Madison? So Madison's asking which side we draw the I minus on. If there was light, it would do a different mechanism, Julia, and we're going to talk about that at the end of the course. No, we don't have any selectivity. You have a carbocation, so you could attack from either the top or the bottom. So if you draw an up wedge, you have to also draw it with a down wedge. But it's also not a chiral center because, or a stereocenter because it's got two methyl groups. So I guess it wouldn't really help. I mean, on that last structure, there's no which side we draw the I minus on. Well, you want to make the carbocation at the more stable place. So heteroatom bonds are really unstable. So iodine, iodine, or iodine, oxygen, or bromine, bromine, or bromine, nitrogen, or basically bonds involving carbon are stable, relatively. So a carbon bond or a carbon hydrogen bond are very stable, but carbon oxygen, carbon nitrogen, hydrogen oxygen, hydrogen nitrogen, those are reasonably stable bonds. Reasonably. These kinds of things, these heteroatom bonds, when you have two things which are not carbon or hydrogen attached to each other, tend to be very reactive bonds. Okay. I want to zoom in on this. So in the case of, if this had been a hydrogen, that is the right structure. If it's an iodine, it's not. What do I mean by that and why? Because the iodine can make 2 bonds. Hydrogen cannot make 2 bonds. This is what it is. This thing exists more like this. We call this an iodonium. And it's kind of like a resonance hybrid. Kind of. It's not resonance. Bonds are breaking and being formed. It's kind of an equilibrium. But it acts like resonance. Now, it doesn't affect, for the most part, the overall chemistry. It still reacts like this guy. Note, that's also the second most stable resonance structure, right? The most stable one would be to have the positive charge on the iodine because everything has its full octet. So it reacts like this guy. But what we really have is a fast equilibrium between these 3 species. Now, for the purposes of right now, this doesn't make a freaking difference that it does this thing that makes these 3-membered rings. It's right to draw it. So if I did this question, we're going to do another question. Slightly different question. So the question I've got is which way? So again, heteroatom bond is going to be the weakest. We have an iodine chlorine bond, but now it's not equal. Which way is that bond polarized? I'm basically asking which of those atoms is more electronegative. Yeah, perfect. Perfect. Good job, Jake and Carolyn and Madison and Kian. So we have that. So if we draw our arrow, we would expect that. And this time, what I'm going to draw so maybe this will help your question, Madison, is the iodine is the one attached. So does it matter where I put it? Yeah, it does, because I point that iodine on first. And what I need to do here is I need to figure out the chlorine. If the chlorine attacks the iodine, I go back to starting materials. Because I reform the chlorine iodine bond, I reform the double bond. But what I need to remember is I need to figure out kind of what is the partial charges here. Where is the charge going to be? Which of these 2 carbons is more reactive? And remember, what we can sort of think about is this thing is an equilibrium. Kind of like a triangle thingy, because everything's a triangle. How did it form a triangle? Well, you could have drawn one of these and then formed the triangle. Yes, Caroline, that's fine. Okay, so what I've done to get here is, let's take it. Let's draw it this way, okay? Does that work a little bit better? Did I unlose you? So why is this happening to me right now? It's me what you're asking. Aren't three-membered rings unstable? Carbon doesn't love them, but iodine is much, much lower down the periodic table. So it looks like right now this iodine looks like it's sp3. It's not. It's using f orbitals and d orbitals, and the angle can be really weird on iodine. Iodine just doesn't give a shit. Iodine's so it can basically not be an equilateral triangle. You can get the bonds on these two guys a lot bigger and really narrow down the iodine bond, and iodine's fine with that. So it doesn't need to be an equilateral triangle. So halogens do this. They make these three-membered rings. Actually, any heteroatom that's next to a carbocation like that is going to make a three-membered ring. Because if you compare this, this carbon is 6 electrons. This iodine is 8 electrons. Everyone's got their full octet. You're going to make this every single time because everyone's got their full octet. But this guy is now going to react with our nucleophile, which is Cl minus. And we need to determine where the Cl minus is going to go. And to do that, we need to know which of those carbons has more positive charge on it. Yeah, so I got that, Carolyn, right? Yeah. Full octet, I plus, full octet, I plus versus a not full octet carbon. Full octet always wins. We've been seeing that with oxygens on resonance structures and stuff. So what we need to figure out is where the bigger partial positive charge is. And it's going to be bigger at the tertiary center because tertiary carbons stabilize positive charges better. So if that positive charge is dispersing over the iodine in both those carbons, the carbon with the biggest positive charge is going to be the tertiary carbon. Good, Hannah and Drake, you both got it. So when we draw the arrow of the nucleophile coming in, it's going to attack that carbon, and we're going to break the carbon-iodine bond because carbon can only make 4 bonds. Equivalently, you could have drawn it from up there when you kind of drew an equilibrium there and sort of said, okay, look, I know this thing's an equilibrium. This is the tertiary carbocation. This one's the more stable one. That's going to be what's going to be attacking for a nucleophile. Both of what I've drawn there in those blue arrows, those are identical in meaning. You can draw either of them. You'll get full marks for either of them. And what it gives us is the product. What's important here is that chlorine is on that carbon and the iodine is on that carbon. And it's because that carbon was more positive and the iodine was added first. And the iodine was added first because the bond is polarized between iodine and chlorine. So like this is, it's inevitable that this happens. There's really no other option. So why is this central carbon the most positive again? It's tertiary hyperconjugation. It's a tertiary versus a primary. And so it's all about hyperconjugation. Okay, there are a metric ton of examples of this on one of the assignments. Might be assignment 1, might be assignment 2. Full answer keys for those. This is good practice. There's also some in the textbook. Strongly recommend you work through these and think about them. What we're doing here is still the same thing. Every step we're dealing with the charge. We're always thinking about the charge and how we can stabilize the charge with what we have available. Yeah. I know it's almost a ridiculous number of things to keep track of at the same time. Like there's geometry and there's all these electrons and there are the atoms there and where the charge stabilized and everything. It's just it's so much information. I get it. It's hard. It it is hard. Practice. It really will start making sense. You'll start going, yeah, of course that happens. And you'll start automating things. It'll become quite easy. But it does take practice. And I don't think there's any way around practicing. Okay. No, I generally won't. So on the assignment, I generally won't. It will be from the reagents. You should be able to figure out what it was. So this asks on the assignment, we specify the type of reaction? No. The reagents specify the type of reaction. Okay. I will see you guys later. And actually, I'm going to hand this over to Samra to carry on. Yeah, Madison, the strongest advice is if you're lost in this, please go practice this. Try and work through it. Sit there with the answer key. Try and work through it. Sit there with some of your friends. Try and work through it. Everyone's going to pick this up at different speeds. I promise. But it does get there. Okay, good luck.